Happy almost afternoon. So, oh awesome, it's up there. Okay. So as usual, I have a few logistics things to kind of quickly cover. First thing is I've kind of bumped back all the quizzes. So there's a bunch of quizzes leading up to the first test. I bumped those back a week because we had the flexibility to do that. And I noticed that we needed a bit more time for that. So quiz 2, so you can see all of that in the assignment page or the syllabus page here. So if you go to quizzes, you will see that quiz 2, that's the next one you all have due, is not due, in fact, until this next, so a week from today. And then the next quiz is a week after that, next quiz is a week after that. And so we will finish up to quiz 4, so including quiz 4 before test 1. Quiz 5 will be after that, but there you go. Those are all updated. Okay, so that's one thing. Second, one thing I'm going to try to do, so clicker questions, unfortunately, it's a little wonky for how I can upload the scores so you all can track your grades in the class. So what I'm going to do is I will upload every individual session, and that'll show up here in clicker questions, this category. And you're going to see here it says 0% of total. So this will not factor into your grade in the course when you're looking at the grades. So when you go to grades, this will not factor into it. But at the very bottom, there's a clicker question total. This is the one that will factor into your grade. This I'll update, instead of like after every class, I'll update this every week. Whereas the other one I'll update after every class. The other ones will show excused. So if you were not able to make it to class due to any kind of medical emergency or any other excused absence, that will not show up here, but it will show up in the other one. And then I'm keeping track of all the excusals. Unfortunately, there's just no way for me to keep track of it here. But at the end of the semester, I will take those into account. And they will show up here just so you can have peace of mind that I have like logged it somewhere. Okay? So that's that. Very last thing, office hours. So as you all know, continuing to hold office hours. I'm trying to figure out the Monday one to move because unfortunately, that's just a weird one. Find your room for that. But one thing I want to stress with office hours is yes, I will certainly help you with any, like my first priority with office hours is supporting you all in learning the content in this class. However, I am happy to talk about anything during my office hours or even if you email me outside of that. While my job first and foremost is to support you all in learning this content, this is not the only part that I would like to support you all in. I'm literally happy to talk about anything from future career interests you're interested in and anything I can give you advice in that area. So for instance, I'm meeting someone about research stuff today and just giving my knowledge in that area. Mental health is a very important area that doesn't get talked about very much. And so if that's an area that you may be running into any challenges with, please, I am happy to talk to you about that and maybe point you in the right directions. There's some limitations of what I can do there, but certainly want to help you out there. Religion, philosophy, whatever. Like, please, I just want you to know that I'm happy to talk about anything. Again, I will prioritize kind of this stuff, so there's other students in there. But I just want you to know that I'm not just a resource for this. I want to support you however I can in whatever aspect of life that may be. I may not have the answers, but maybe hopefully I can point you in the right direction if I don't have the exact answer. So, just to keep that in mind, your all's lives, this is just physics content. Your lives are much more complex than that, and if I can support you in those other areas, I would be happy to, but I'm not going to force that on you. So yeah, just wanted to mention that. Okay, so today, reminder, we started Gauss's Law. I told you all that normally we go through Gauss's Law and I do the whole thing, and I told you all this semester is going to be slightly different. I'm not going to have you all solve the complete Gauss's Law problems, but we're going to do the parts of them. I'm still going to assess you on flux, I'm going to assess you on being able to find charge enclosed. But putting it all together, I'm not going to worry about as much because none of you are really going to use it except for physics majors. If you are a physics major and you're interested more about this, please let me know. We can talk more. I will show some examples of it in class, a couple more of them. But I'm not going to assess you all on it just because it takes too much time and I think it has little gain for the vast majority of you. Okay. So, all that to say, last time we did talk about different... this was kind of one of the important things. So we talked about flux before, then we started talking about charge distributions. I said there's basically 3 different ways charge can be distributed, whether that's linearly, so 1D. Technically, I guess we already did 0D. 0-dimensional is a point charge because it doesn't have any thickness or dimensions to it. It just exists at a spot, so that's 0D. 1D is a line of charge, 2D is a plane of charge, 3D is a volume of charge. So today we're going to get some practice with calculating. Basically, an example would be this one I showed here. If I said, here's a sphere, it has this much charge, it has this much volume. How much charge is enclosed by the smaller sphere? We're going to practice that some today, and that's going to kind of conclude that, and a couple other things will conclude our time with this, and we'll move on to potential. Okay, so here it is. I'm going to start you all off with seeing if you can remember how to do it. So what is the charge density in a sphere with radius 5 meters and a total charge this distributed uniformly throughout its volume? Forgot to clarify that because this charge could be distributed on its surface. This charge could be distributed non-uniformly. There could be have more in the center and less on the outside. All depends. So you all get to practice this, and if you have your computer, you can look up the slides and see the previous slide, and that'll give you some of the equations for it, or maybe you wrote it down from last class. If you need to, Google it. Do whatever, use whatever resources you need to use. Talk to your neighbors. Yeah, and it's not working. So if you just write down the answers, just hand it to me, I'll put them in. If you just, I trust you. Just put them down, and then just at the end of class, just make sure your name's on it. That way I can actually link it to you. Alright, I'm still missing most of them, so I'm going to give you all about like 30 more seconds or so. If I need to give more time, I'll give more time. If you're having challenges with this and you need a hint, charge density is how much charge, in this case volume, how much charge per meter cubed. Alright, I'm going to give you all about 10 more seconds. I don't know how many of you are, but it seems like we're kind of nearing. Just so we can continue moving forward. Alright, so 5, 4, 3, 2, 1. Okay. So, how are we going to go about this problem? Well, just to go through the steps, the problem-solving steps, what are we trying to find? We are trying to find the charge density, so that is the unknown charge density. And so that's so charge density given a sphere with radius 5 meters and total charge 3.6 Newton, or not Newton coulombs, nanocoulombs, distributed uniformly throughout its volume. So I'll draw my picture. There it is, and this thing has a charge, so a capital Q, of 3.6 nanocoulombs. That is 3.6 times 10 to the minus 9 coulombs. Nano is times 10 to the minus 9. If you don't remember that, that's one that you're going to want to put on your formula sheet because we're going to be seeing nano a lot. And then it has a radius r, which is equal to 5 meters. Okay, so how do we solve this problem? Oh, and it's important to note that this charge is distributed uniformly. I said it's positive, so it's going to be a positive charge throughout its volume. So the visual for this is that we are lacking electrons throughout the entire thing, or we have excess protons throughout the entire thing. So we go back to our previous slide, because this is the one that shows kind of all the charge densities. This is the charge density slide. And so we look at our thing and we say, is it a one-dimensional object? No. Is it or I should say, is the charge distributed one-dimensionally? No, because it's not a line distribution. Is it distributed over the surface? No, because I said it was distributed throughout the volume. So then we have to go to the third one, and that is our volume charge density, which says that our charge is distributed uniformly throughout the volume. So we say, great. And then I gave you the equation here for that, where rho, that kind of italicized P, gives us an equation for that, the charge divided by the volume. Because that gives you how much charge there is per volume. Okay? So we write that out. Rho equals charge over volume. We then have to remember that the volume of our shape depends on what kind of shape we have. If I'd given you a cylinder, it will be different than a cube. It will be different than whatever else. This is a sphere. So the volume of a sphere is 4/3 pi r cubed, where we use the radius of the sphere itself. We then know what Q is because I already have that up there. So it's going to be 3.6 e to the minus 9 coulombs over 4/3 pi 5 meters cubed. And then that's going to end up giving you 6.875 e to the minus 12 coulombs per meter cubed. And this is This is one way to kind of check if your equation made sense. All my answers I gave you were coulombs over meters cubed. So if you were using an area, you would have had a squared down here instead of a cubed, and you wouldn't get the right units. This is something called dimensional analysis, so you can use this to check your answers. The units that you finally get should make sense. If they don't come out to the units you expect, then you probably messed up the math somewhere or used the wrong equation. So that's one way to check your answers. Check the units, make certain they make sense. Okay. Before moving to the next one, so the next problem, I'll go ahead and show it to you. I'm not going to have you all solve this yet. I'm going to give you an example. I'm going to work through it, and then I'm going to have you all do this. So this problem is basically the exact same one, where I have a sphere with a radius 5 meters and total charge 3.6 nanocoulombs. I'm going to copy that same thing, distributed throughout its volume. Make certain all those details are there. But the difference with this problem is, instead of asking for the volume charge density, we already did that, I'm asking you what is the charge enclosed for a spherical Gaussian surface with radius 3 meters that is located at the same center as the charged sphere. So hold that in your brain, and I'll even show you the picture, basically what this looks like, because we have some jargon here. So here's our sphere, which has a radius r. I'm asking you how much charge is enclosed in a sphere that is centered at the same spot, but with radius 3 meters. So we'll call this little r 3 meters. I'm doing these problems because this is an important skill that you're going to have to use, both with mass is more commonly where you're going to see this, where you have some amount of something and you're taking a subset of it and you need to figure out how much of that subset you have compared to the whole. So this skill will extend outside of this charge distribution stuff. So there you go. Now that you have that in your brain, that's the problem you're going to need to do. I will give you an example problem where I will actually do. So I have a plane of charge with charge 3 nanocoulombs distributed uniformly over its surface. How much charge is enclosed by the Gaussian surface shown below? I'm putting shown below because it's going to be a little tricky for me to word what this looks like. So just for the sake of time. So I will draw now the picture so we have a reference. Here is my plane of charge. We imagine this plane is infinite. Well, actually we don't need to. It doesn't matter if it's infinite right now. I will give you the dimensions of it is 5 meters by 3 meters. And what we're going to try to find is the amount of charge enclosed. Our Gaussian surface is going to be a cylinder. I specifically am choosing this geometry because it's what we're going to use later. We're going to see it later on, so this will hopefully just kind of prime you for that. So we're choosing a cylinder. So how much charge is enclosed by that cylinder? The part you have to kind of see here is, remember, the thing with charge is this plane. This plane is the thing with charge, and it has positive charge distributed uniformly across. Q equals 3 e to the minus 9 coulombs, 3 nanocoulombs. So the question is basically, how much charge is enclosed by this object? How much of the plane is included inside this object? This is how much. That circle shape. Now you may want to use the volume of the cylinder, but that's not, this volume up here is in space with no charge in it. The only place in this cylinder I've drawn with charge is this flat surface where the plane is. Okay, so that's kind of an important concept. So how we're going to solve this problem is basically we're going to find sigma. Remember, sigma is the charge density, and against this case, it's a surface charge density because it's a flat 2D surface. So we look at our other, if we look to the other slide, we'd see it's Q over A, so total charge of the plane divided by A. Again, this is true because it's uniform. If it wasn't uniform, you'd have to do an integral, but we're not going to worry about that. Once you have this, this tells you the charge per meter squared. Per meter squared. So how much charge I have per meter squared. So then the idea is how many meters squared are enclosed by this object. How much area do I have in this shaded in area? So step 1, step 2, how much charge or how much area enclosed by cylinder? Well, it is just going to be the area of a circle, so I would tell you that this radius, well actually we'll put it even at the top. R equals, let's just say 0.2 meters. I'm just making up numbers here, it doesn't really matter. In this problem it would matter when you actually plug stuff in, but since I'm making the problem I can do what I want. So area is going to equal of a circle, which is pi r squared. So I had to know it was a circle by looking at my picture. I had to know it wasn't volume because there isn't, again, there isn't charge at the top of the cylinder. There isn't charge at the bottom of the cylinder. The only place there's charge is the plane. The Gaussian surface does not make charge. The Gaussian surface is just this imaginary object that we enclose our thing with to figure out how much charge is in it. Okay? So I'm going to copy and paste all of my wonderful work here to another slide to give me more space. And we're going to solve the problem. So many boxes. It's fine. It's great. Up there. Okay. So we have our process for solving it. We find the charge density. We then multiply. What we will then do is we're going to use, ironically, the same, well, not ironically, I don't know. You can say it's ironic. I don't really know. Q enclosed will be the sigma. We use the exact same equation, but because everywhere the charge density is going to be uniform, so the charge density in here is the same as the charge density out here, so you're then working backwards with the same equation. So therefore Q enclosed will be sigma times the area. The area, I'm going to say enclosed. In our case it's a circle. So at this point it's just plugging and chugging. I can even, so I'll set up my, so sigma equals Q over A, so I'll just plug those out. So Q over A, which equals 3 e to the minus 9 over, our area here is a square because I'm finding the charge, the charge distribution throughout the entire object. I know the charge across the entire object, so I have to use the entire object. So this one is area of square, or area of plane. Okay, it's a rectangle, so it's just going to be 5 times 3. Okay, that gives me a number. I'll just find out what that number is. Make my life easier. This is a good chance. Check your calculator skills. I always recommend whenever I'm doing something in a calculator, you do it as well, because you need to know how to use your calculator well and get as much practice as you can. Because I don't want you missing points because of just silly mistakes on a calculator. Units, coulombs per meter squared. Great, there it is. So that's step 1. Step 2, I then take this, so I say, I'm going to use that Q enclosed equals sigma times area enclosed equals 2 e to the minus 10 coulombs per meter squared times pi, and my r in this case is 0.2 meters squared. Important thing here, again, you can check if your equation's right, because this meter squared should cancel with this meter squared, because my final answer is coulombs. It's charged, so it should be coulombs. If you're not getting coulombs out, you set it up wrong. Again, really nice way to check your answers. And again, this is a skill that you're going to carry through to the rest of your classes. You can check your units, and if that, again, just engineering, you're going to be doing that a lot. All right. There it is, 2.51 e to the minus 11 coulombs. That's our final answer. That is the charge enclosed by this cylinder. One way to finally check your answer is if you got a number that is bigger than your original charge. That is wrong, because that means that you have more charge enclosed than the entire thing has, and that just doesn't make sense. You can't enclose more charge than you have. So all these little checks are good. Because sometimes we just make really small mathematical mistakes. So don't want to be doing that. It's especially important in engineering because you are actually making real world things, and if you use the wrong number, things break, and that's expensive or dangerous or whatever. Far more important in engineering than physics. We just keep it as variables so you can't mess up the calculations.
So you use the charge density in the first part?
Yep, because the charge density, because it's uniform, this is the charge per meter squared, and because it's uniform, that should be the same everywhere. Think of it like a piece of iron. A piece of iron should have the same mass per volume everywhere in it, assuming it's a uniform piece of iron. If it was maybe more dense on one side, that would change. But if this charge density changed, that would mean that you have more positive charges in some area than you do in another per meter squared. So definitely think on that some more. All right, now you get to practice. I did an example for you. It was a 2D problem. Now you have to do the 3D one. You've already done one step of this. But to reiterate the problem, I have a sphere of radius 5 meters, total charge 3.6 nanocoulombs, which is distributed uniformly throughout its volume. What is the charge enclosed if I use a spherical Gaussian surface, so again this imaginary object, which is enclosing an amount of volume that is 3 meters from the center of it. So a sphere that is 3 meters from the center of the actual object. How much charge is enclosed by this imaginary shape? The answer is A, I have 1.3 e to the minus 9 C, 1.3 e to the minus 9 Q, 7.78 e to the minus 10 C, and 7.78 e to the minus 10 Q. What's the answer? Alright, we need to go about 30 more seconds. So we can get some answers here and then continue on with the rest of our stuff. A couple more things we need to cover before we finish class today. Alright, so about 5 more seconds. So 5, 4, 3, 2, 1. Okay. So, reminder for this problem, we're going to do that same two-step process that we did in the last one. Step 1, find charge density. Step 2, multiply charge density by, in this case, it's volume enclosed. Last one was area enclosed because you had a 2D object, you enclosed the 2D amount of charge. But it can be volume, it could be linear, a line. In this case, it's volume. I'll make it lowercase. There's no reason why that B should be uppercase. Okay. By volume enclosed. Okay, so let's go ahead and do it. Again, I'm going to kind of copy and paste this into the next slide to give me more room. Okay, I'm going to shove this in the corner. All right. So, our first question is, what kind of charge density do we have? Do we have linear, surface, or volume? Well, I said it's distributed uniformly. Again, you already did number 1. But I'm going to kind of write it out because you'll see that there's a little bit of a shortcut we could do to make our math easier. So you get Q over 4/3 pi capital R cubed. Now I'm going to leave it in terms of the variables because I'm just going to show you all that sometimes when you leave things in terms of variables, it can make your life easier and your math easier. You could have just used the calculation we did here. You could have just used that value, done. But we're going to kind of just leave it as variables for now, and you'll see it's way nicer when you do. Okay, so now we do charge enclosed equals rho times volume enclosed. So you're going to get rho times 4/3 pi little r cubed. I now know what rho is, so I'm going to plug that in, and you get Q over 4/3 pi big R cubed times 4/3 pi little r cubed. This in the numerator, this in the denominator, so I can cancel out 4/3 and pi. I can cancel out 4/3 and pi. And you get Q times R over capital R cubed. They're both cubed, so it's like little r cubed over big R cubed. I can pull out that cubed here. Same thing. That is much easier to solve than putting in 4/3 pi, 4/3 pi. Again, you can do it if you want to. It works just as well. But this is one of the benefits of just leaving things in variables as long as you can. It sometimes makes the math way easier to calculate and just makes your algebra mistakes less likely to happen. So we plug in our values, 3.6 e to the minus 9 coulombs times 3 meters over 5 meters cubed. Another nice thing about this is if I gave this in terms of like millimeters and millimeters, those millimeters would have canceled. Again, it just makes your life easier mathematically. And you get 7.78 e to the minus 10. Remember the units as coulombs. I again purposely put C and Q here because Q is the variable we use for it, but it is not the unit. So, again, A lot of extra steps there, but there you go. A lot of practice there. In the problem sets, there's more practice. Please make certain you know how to do this because this is a skill that's going to translate not just in this class, but anytime you deal with mass. Like, this is a very important skill that you should know how to do. Is given a big thing, how do I find how much I have of a subset of it? So, useful skill. Okay, great. Let me go ahead and mark the right answer there. Again, most of y'all got it right. If you did not, that's okay. Just check why you got it wrong and make certain you understand why that was. If you don't, please ask me more questions. Okay, so this is funny because I asked you all this question at some point previously where I was like, hey, if you had a line of charge, what would it look like? How would you actually do it? How would you find the electric field due to a bunch of tiny point charges? So this is, again, just a conceptual kind of question. I have an infinite line of charge, so imagine it goes forever, and I have a point P. So this is infinite, so it goes as much to the left as it does to the right, the charge does. My point P is below it, and I'm asking you for the direction of the electric field at point P. So use some of the skills that you've seen with electric fields. See if you can figure out this direction. This is an important skill that you should be able to do. If you can't do it now, that's fine. Again, that's why we're doing it. Alright, just missing a few responses, so give you all about a few more seconds. Alright, gonna close it out in 5, 4, 3, 2, 1. Okay, so remember the process that we came up for doing this? The way we kind of conceptualized how to do it was you treat it as a bunch of point charges and we find the electric field due to each one, add them all up. So we'll consider this one here. So that one, we'll call that one 1, makes an electric field down. Let's call this one 2 and this one 3. And I'm not going to do every single one because there's a bajillion of them. Electric fields point away, this one points away. And you can see here that the x components, due to symmetry, are going to cancel. So 2 and 3 are going to add to just get you down. That process will repeat all the way down. So the answer is B. And this is a symmetry kind of problem. So this is a useful skill to be able to identify symmetry and recognize that a complex problem gives you a pretty simple answer if you know how to kind of go about it. So the reason we are doing this is because, again, I'm not going to have you all do this, but I still want to quickly talk about it. So the electric field due to a line of charge is always going to point away from it. So for instance, if I said find the electric field at some point out here, out of the board, directly kind of in front of it, it's going to point directly away from it. So the electric field will point towards you all. If I picked a point that was a little bit out of the board, directly in front of this line of charge, if I picked one above it, it'd point directly up. If I picked one kind of in the board, directly behind it, it'd point into the board. The reason this is useful is because if we chose a Gaussian surface for this, remember when we're doing Gauss's law, we have to evaluate that integral of E dot dA. So we have to sum up the electric fields times the area vector, and the angle between them matters. But the nice thing is when we choose a cylinder, so if I pick a point here on top, the electric field points up. If I pick a point here on the right, it's going to point that way. If I pick one here on the bottom, below it, it points down. The area vector, though, remember that way of doing area vector? So my water bottle, if I want the area vector in the top, I just put my eraser flat on it. The area vector points up on the top. On the side facing you all, the area vector points towards you. On the bottom, it points down. So the consequence is that the area vector points in the same exact direction as the electric field at every single spot on this outer rolling part of the cylinder. The consequence is that the angle is 0, so you just get E times the area of this outside, well, the area, and we're specifically doing the area of the outside of this, so that is going to be pi r squared times L. One way to remember the area of an outside of this thing, oh sorry, it's not pi r squared times L, it's 2 pi r. So I actually don't just have this equation memorized, I kind of derive it in my head every time, which is maybe a bit more work than I need to do. But it's a useful trick. Remember that the area on the outside of this is basically a bunch of circles. How many circles do I have? I have L circles. So one of these circles makes 2 pi r. I have L of those. That's how I do it in my head. Next thing, we have to do the whole area. So we're summing over the entire area. So we've done the outside rolly part. What about these sides? Well, grab my water bottle again, the area vector. So for the side on the right of the, nope, left. On the left of it, you see the area vector. Again, I put my pencil there. It points to the left. So in this case, it kind of points this way. But the electric field at every point here is going to be perpendicular to that. Remember, this is dot product, so it's E times dA times cosine of theta. If they're perpendicular, that angle is 90. Cosine of 90 is 0. So the E dot dA on these flat sides, there's two sides of it, is 0. So so this is the rounded side, flat side, E dot dA equals 0. So I went through all this process just to show you that when we're doing Gauss's law, we choose shapes that are convenient. We choose shapes so we don't have to do integrals. Okay, that was the whole purpose of that. If you see Gauss's law in the future, physics majors you will, math majors you may at least see it mathematically used as some tool, but this is the concept of it. So for a line of charge, we choose a cylinder. For a sphere, we chose a sphere. And the last one I want to quickly talk to you all about, yeah, here we go. Have you all do this, and this is kind of, we'll be nearing the end. What is the direction of electric field? We're going to find the shape that we'll choose for a flat surface, and then we'll talk about very quickly why it's that. So I have here an infinite plane of charge, which has charge distributed uniformly on the surface. So we imagine this is a piece of paper that goes to infinity in every direction, but it has 0 thickness. And I have here a point that is directly above this flat piece of paper. And I'm asking you, what is the direction of the electric field at this point? Response A is upwards, response B is downwards, C is down and to the right, D is up and to the left. What is the direction of the electric field at point P? My hint, use symmetry. And we're going to use this to determine what shape we should use. And this result is going to be very important when we move into capacitors. So this one is the most important out of all of them, as far as you all needing to know it. So infinite number of charges to the left, infinite number to the right, infinite into the board, infinite out of the board. Completely symmetrical on all sides. All right. Give you all like 5 more seconds, just missing a handful of people. So 5, 4, 3, 2, 1. Okay, so we're gonna do this problem the exact same way we did the line charge. We pick a point right below it, because we're gonna start there. That one points up. So the one right below it, we pick one slightly to the left, and we pick another one the same distance to the right. So the one to the left, make an electric field up and to the right. One to the right, we'll make one up and to the left. The same thing if I picked one now slightly down and slightly up. That's a little hard to draw, but one of them will point out of the board upwards, the other will point out of the board or into the board upwards. I'll attempt to draw this, it's gonna be terrible. That way and that way. Basically, the long and short of it is all the x and y components are gonna cancel, because for every charge on the left, every charge on one side you have another charge on the other side. That's gonna cancel those components. The only thing you have left is this A. There you go. Make certain that makes sense. If it doesn't, that's okay. We can talk more. But the important part with this problem and the one we did before is I gave you nothing about P. I didn't tell you where it was. I didn't say it was really close. I didn't say it was really far. I didn't say it was more to the left or to the right. Again, this is an infinite plane, so who cares where it is? It's going to be uniform on every side. It's infinite to the left, infinite to the right, infinite up and down. So this is just an arbitrary point. Arbitrary meaning I could have literally, doesn't matter. If I told you the point was here, if I told you the point was here, if I told you the point was way up here, if I told you the point was really close, the electric field is all going to be upwards at every single point. This is really important. So I'm going to move into what shape we choose. It's a cylinder. So hence why I did that example to you for charge enclosed for a cylinder or for a plane of charge, and I used the cylinder. The explanation being the area vector on those flat ends now is in the same direction. So the area vector, the one that's closer to you all, points outward, and the electric field points outward. On the flip end of it, the electric field points into the board, and the area vector points the same way. But the area vectors on the rounded sides point perpendicular to the electric field. So again, when I do that summation, so an integral is just summing up all these area vectors. Flat sides, you get to pull out E, and you get dA, so the integral of dA. Well, I have two sides, so what is the area of this side plus the area of that side? That is going to be E times 2 times pi r squared. So it's pi r squared because it's the area of a circle. That's what the flat side, that's how much area is there. And I have two of them. So pi r squared plus pi r squared is 2 pi r squared. Rounded sides, the integral of E dot dA equals 0 since E perpendicular to dA. Okay, so we choose a cylinder. We're going to use this. The result, and you know what? Yeah, I'm just going to solve it out for you all. Let me see if I have a slide that already does that. If not, I'm going to do it. Okay, technically it's here. I'll do it in front of you all. So it's there in writing, but just for your own thing. So the reason I'm going through this solution is because maybe you've heard of capacitors. If you haven't, we're going to cover those, and those are a very important electrical component. And a capacitor is two of these planes. It is two planes, one positively charged, one negatively charged, both flat, kind of like just hovering over each other. So if we want to find the electric field in that, this is how we do it. So we have a plane, and it has some positive charge distribution. So it's got Q, and then it's got some area. So it's got a Q and it's got an area. We're just going to call those arbitrary. I can make up numbers for you, but we're going to leave it as Q and A for now. And you'll see why. So here's my cylinder. That's what we chose to use. So we're going to do Gauss's law. I'm doing this to derive the final expression, which you will be using. So that's why we need to do it. So remember, Gauss's law is E dot dA equals Q enclosed over epsilon naught. Okay? So we're going to treat these, this is going to be part A and that's going to be part B. Remember, the purpose of Gauss's law is to find electric field. This is what we care about. That's the whole reason we're doing this. What we're solving for. We don't know what it is yet, hence why we're solving for it. So, part A. We need to find the integral of E dot dA. Well, I just told you all before that on the flat sides, flat E dot dA is just going to be E times 2 pi r squared. That's the flat sides. On the rounded sides of that shape, rounded sides, E integral of dot dA equals 0. Okay, great. Done, quick. We just did that in the last one. Reminder, pi r squared comes from the area up here and the area down here added together. Okay, part A done. Part B, this is where we're going to need to use that charge enclosed skills that we talked about before. So step 1 of that is sigma equals Q over A. Step 2, and again we did this before, but I'm going to go through some of the steps just quicker this time. If you don't remember, please look at the other slides. We say that Q enclosed equals sigma times area enclosed. And remember that area enclosed, I'll use blue, is this one. So I'll kind of mark these. So 2 flat sides, blue flat circle. I don't know. Hopefully that helps with tracking it when you're looking at this later. So it's just going to be sigma times pi r squared. Interestingly, it's the exact same r because it's a cylinder, so this circle here has the same radius as this circle. So that's r, and that's r. Same exact circle, same exact radius. There you go. So last step, A equals B. So let's just plug those in. So E times 2 pi r squared equals Q enclosed, which we just said, and I guess let me write this. We're going to leave it as sigma for now. I'm just going to leave that sigma equals Q over A because you'll find that we can't actually reduce it anymore. And our final result we kind of want in this way. So Q enclosed is just sigma times pi r squared over epsilon naught. So E equals sigma times pi r squared over epsilon naught times 2 pi r squared. Look at that. Pi r squared cancels. And you get this really interesting result. You may be like, this isn't interesting at all. Well, that's your opinion. It's really interesting because there is no distance requirements here. That's the part that is kind of, I'm going to use the word profound. That's the part that we really care about profound. The electric field does not matter where you are. It doesn't matter whether you're here, doesn't matter whether you're here, doesn't matter whether you're super far away. Again, this is for an infinite plane. You may wonder, infinite planes don't exist, but what I will challenge you all to kind of think about is imagine this board, even just take the dimensions on that. If my face is this close to it, my nose is right up to it, I can't see the edges of it. So conceptually, it might as well be infinite. When you're close enough to something, you can approximate as infinite. So sigma is the charge density. You may have to calculate that in the problem, maybe given to you. Yeah, let me answer this question before you all head out. We still have 2 minutes. So, where did epsilon naught come from? So this is the reminder. This is what Gauss's law just looks like. So it's the integral of E dot dA equals Q enclosed over epsilon naught. So that's just the form of the equation. And epsilon naught represents the permittivity of free space. It's a constant. It is 8.854 e to the minus 12. The units I have to kind of quickly come up with my head. I'll write those later. But it has a meaning, but that comes from the original equation. We will use this equation for capacitors. And again, capacitors are very important. We're going to kind of hash those out a lot. Pretty much every single one of you needs to know that for your future life. Obviously, electrical engineers, you need to know that. Mechanical engineers, just all of you, if you're working with circuitry, capacitors, resistors, inductors are the foundation of circuitry. So we have to know this to be able to do actually useful stuff with it. All right, you're good to go. That's the basic. That's the end. We're basically done with Gauss's law. So you know everything you need to know now to do all the problems. Thank you.
Hi, how are you?
Good. Let me close this real quick.
Question.
Yeah, sure.
So you said the distance doesn't matter, right?